Hi, I'm Daniel Chan from UNSW Sydney. This is Extension 3 Mathematics for talented high school students. In this video, I want to tell you about a very interesting counting problem. And this counting problem, which is related to the idea of counting monomials, has a very interesting interpretation using generating functions. In its simplest form, we can look at the question in this way. Okay, so we're going to consider the following equation for each and every natural number n. Okay, so for each natural number n, we just look at a, b, c, whose sum is equal to n. And these a, b, c's, they're not allowed to be any number. These a, b, and c all have to be natural numbers, so non-negative integers. So we'll look at this equation and we'll look at all these solutions, and for each n, we're just going to count the number of these natural number solutions to this equation. Okay, so let's just have a look at some of the earlier terms for this. So what's u0? So u0 I claim is equal to 1, because the only possible solution to this equation with n equals 0, if a, b, and c have to be non-negative integers, is 0 plus 0 plus 0 is equal to 0. Okay, so let's look at something a little bit more interesting. What's u1 equal to? So what's the number of solutions to a plus b plus c equals 1 if a, b, and c have to be non-negative integers? Well, I claim it has to be 3 possible solutions to that. So a can equal 1, in which case b and c are both 0, or b can equal 1, so you get 0 plus 1 plus 0, or you can have 0 plus 0 plus 1. And they're of course the only 3 possibilities, because each of these, since they're all non-negative, each of these have to be less than or equal to n. And once one of them is equal to n, so one of them in this case is equal to 1, okay, then the other 2 have to be 0. So there are 3 possibilities. But what's the general answer? Now you can answer this question in lots of different ways, but there's a very interesting way of viewing this via generating functions that I want to show you, and it involves a related question of counting monomials. So let's just see what's going on here. So I'm going to present to you the answer in a very interesting way. So what I'm going to do is I'm going to look at the solutions. Solutions a, b, c, it's a triple of non-negative integers, correspond to something called monic monomials in some variables x, y, z. So in this case, what's the corresponding monic monomial? And then I'll tell you what monic monomials are. It's x to the a, y to the b, z to the c. So this expression here, it's like a polynomial. You're looking at powers of variables, okay, in this case x, y, and z, and you can multiply them together, okay. If you just multiply powers of the x, y, and z together, and you get something like that, just a single term, okay, you don't take sums of these things, then you get what's called a monomial. Okay, if you take sums of these types of things, you get a polynomial, and also in that case you can allow coefficients. Monic means that the coefficient here is equal to 1. Okay, so here we want to look at, of course, just non-negative integer powers of x, y, and z, and that's why they correspond to this a, b, c natural numbers. And the key point here is that this condition here, a plus b plus c equals n, this corresponds to the total degree. Total degree n. And total degree just means that you sum up a plus b plus c. Okay? So that's what you have there. Okay, so what's the next thing we're going to do now? We're going to do something that's rather interesting, actually. So we're going to look at the following function, p of x, y, z. I'm just going to define it, and it looks like it comes out of a hat at the moment. So it's going to be 1 on 1 minus x times 1 on 1 minus y times 1 on 1 minus z. And then what we'll do is that we'll write each of these, they're the sum of an infinite geometric progression. So it's 1 plus x squared plus so forth. That's the first one. And we do the same for the second one, 1 plus y squared plus so forth. And then last one, 1 plus z squared plus and so on. Now these are each of them power series, and they will converge for values of x, y, and z whose absolute value is less than 1. And we can take the Cauchy product of them, of these two power series, and that gives us a new formula. Now it's no longer power series in one variable to two variables, but as a function, okay, what you will get is something that will converge for small enough values of x, y, and z to whatever this function is. So let's just work out what that is going to be, okay, the Cauchy product, okay. So the first thing that you get, you'll get 1 times 1 times this 1, so you get a 1 here. And what about the term that's the next one in the series? So what you'll have here is you'll have, well, you get x times 1 times 1. And then you'll also get 1 times y times 1. And then you also get 1 times 1 times z. And what's the next term? To get the next term along, so normally when you have the next term, well, if you look at the next term here, when you just multiply two of them, you'll get 1 times y squared, x times y, and x squared times 1. So they're the total degree two terms in x and y. And those ones you have to multiply by 1, so we'll get all of them. So maybe we'll write all of them. X squared plus xy plus y squared. But you'll also have terms like, well, now you can multiply x times z, y times z. And then you'll have also z squared times 1 times 1. And if you look and see what's happening here, what have you picked up here? You've basically picked up all the monic, each of the terms here will be a monic monomial in x, y, z, whose total degree is 2. Okay, so each of these will correspond to a solution to a plus b plus c equals 2. And each of the terms here will correspond to a solution to a plus b plus c equals 1. And so forth. So what you get here is the following. What we'll do is we'll look at p of x, x, x. So what's that equal to? So the first one, that's just 1, that's u0. Plus, and what's the next term here? So we're going to replace y and z with x's now, so you get 3 x's. So that's the x term. And the number of them is, well, of course, it's 1 for every monic monomial of total degree 1. In other words, 1 for every solution to a plus b plus c equals 1. So that's u1 of them. And what do we have here? Okay, if we replace y and z with x, okay, then we'll get these 6 terms. And what do they correspond to? Well, each of these 6 terms correspond to the 6 monic monomials in x, y, and z of total degree 2. And each of them corresponds to a solution to a plus b plus c equals 2. So the number of these terms here is equal to u2. And when we replace y and z with x, they all become equal to x squared, of which there are u2 of them. And so what we've amazingly found here is that this p of x, x, x is equal to what? It's the generating function for this sequence. Okay, if we make a sequence for all natural numbers, we'll let un equal this number of solutions to this problem here. We found the generating function for it. It's just gotten from this by replacing y and z with x. So let's do that right now and see what we get. So what's that equal to? So that's equal to, so you have 1 on 1 minus x times 1 on 1 minus x times 1 on 1 minus x. That's 1 minus x to the negative 3. Of course, this is rather wonderful. Okay, this should contain all the information about this power series. So we just need to find how to expand this as a power series. and then extract the coefficients to get what all these UNs are, and then we've solved this question. So let's see what you have here. So in this case, what you will find is that this is equal to, what do you do here? You use the binomial formula. So the binomial coefficients that will come up are minus 3 choose n, but the better way to write this, of course, is the sum from n equals 0 to infinity of n plus 2 choose n of x to the n. So that's what the binomial series tells you. So if you're good with your power series, and in particular here, you're looking at the binomial series, which is very, very important in enumerative combinatorics, you'll find that this is the power series expansion of 1 minus x to the minus 3. And now you just can equate coefficients. So you just equate the coefficients of x to the n with what's here. So remember, to have two power series to be the same, if they represent the same function, they must have the same coefficients. And the reason why is that these coefficients are basically just given by the derivatives of this function at 0. Okay, so since it's a fixed function and that you have set there, all its derivatives at 0 also given, and so if they're the same, then these coefficients have to be the same. So that means that un equals n plus 2 choose n. And that gives you the wonderful answer to this question. Okay, if you want to say how many non-negative integer solutions are there to a plus b plus c equals n, you find that the answer is un equals n plus 2 choose n. I hope now you can take this idea of generating functions and prove more generally how many solutions are there if you want to sum k non-negative integers equal to n.